valves to control it. So we are discarding that option, which would have been great. The next option is, well, why can't we just store some water that's at the right elevation? So why can't we design these filter boxes so that they're deep enough so that they can lift the water back up into a storage tank? And I have a little schematic of that on the right. And the filters slowly fill that box up with water as they're filtering it. And then of course, excess water goes to the town, but they make that storage tank full. And then when it's time to backwash, you draw water from that storage tank to backwash the filter. And this also seems like a very nice idea, but if you do the math and you figure out how big does that storage box have to be, it turns out it ends up needing to be bigger than an agua clara plant, just to store the water to clean one filter. And so that ends up not being a great option. So we're down to nothing works. We can't think of any options that actually are viable. And so that's why we go with, we have to invent something new. So why is this difficult? It's because of backwash. It's because we need to clean these filters. And the underlying issue is that there's a big difference between the flow rate during backwash and the flow rate during filtration. You need to have a lot of water, a high flow rate, in order to lift all that sand. So if we could somehow get the filtration velocity and the backwash velocity to be closer to being the same, then we wouldn't need a set of 6 filters. But that's not easy either. So it's invention time. So what we're going to do is we're going to do a little geometric trick. So on the left is the design by Sepis, where they have 6 filters working together, 5 of them backwashing 1. And on the right is this idea of, instead of having these 6 filters set out side by side, let's put them on top of each other. So there's the idea of stack. Let's put all those filters on top of each other and put them all inside one box. And then there's some craziness, as you can see. There's water entering in this top inlet. There's water entering in a middle inlet here, another middle inlet, and then a bottom inlet. And then the water, in all cases, the water flows through one small layer of sand and then exits through an outlet. So there's water exiting here, here, and here. So that's this idea of stacking the filters where there's maybe, we use 1.2 meters of sand in that filter box, and each filter is actually 20 centimeters. There's 6 of them all working in parallel when it's filtration time. And then when you backwash, you change it so that you turn off all the inlets and outlets. So there's no arrows shown on any of these inlets or outlets because somehow we've turned them off. And all the water is going in through the bottom. And so now the same amount of water that we had going into this filter before, instead of it going into 4 inlets and going through 6 layers of sand in parallel, it's now all going in through 1 inlet, and it's going through all the sand in series. So you see how we switched it? We went from 6 filters in parallel to, during backwash, it's 6 in series. So the water is going through all of them. And so the water is going through 6 times faster, and we've got our backwash velocity. I'm ready for a question if anybody wants to hit me with one. Are you good with the little trick of switching between parallel flow and series flow? And then maybe the mystery is, how do you inject water into a sand bed? Okay, and then on this slide, I'm addressing another issue, which is, well, where do you get the water to backwash it? And we're going to play another trick because it just makes it so much simpler. Instead of using filtered water to backwash this filter, we're going to use the same water that we would normally be filtering to backwash it, meaning that we're using clarified water to backwash it. And you might say, oh, but the clarified water is not really clean. Well, but actually the clarified water has a turbidity that's somewhere around 1 NTU. And in some parts of the world, like in Honduras, 5 NTU is the drinking water standard. So it's below the drinking water standard in many parts of the world. And I've had water that was just flocculated, flock filtered, and settled to drink. And there, we actually have some towns in Honduras that is the only treatment. They don't actually have water, they don't have filtration, they just have flocculation, flock filters, and sedimentation followed by, sedimentation followed by disinfection. So we're using pretty clean water to backwash this filter, and then we will filter to waste after backwash so that you dump the very first water coming out of the filter. And it turns out, and you can check my math on this, but the fluid residence time, the water residence time in the filter when you're in filtration mode is just, I think just a little bit over a minute or just a little bit under a minute. It's right around a minute. So it doesn't take long at all to flush the previous water that was in the filter out after backwash. And so the fact that you used settled or clarified water as your source water for backwash is not a problem. This filter has the same flow rate and water source during filtration and backwash. You don't need any storage tank at all to backwash the filter. The water that's coming from your clarifier is what you're using to backwash the filter. So here's the whole water treatment plant with the filter tucked in there. So let's trace what's happening in the plant. Here are coagulant and chlorine stock tanks that are elevated so that they're at a high enough level so that they can be pushing those chemicals through our dose controlling system and can be dosing the coagulant up into the pipe leading away from the linear flow orifice meter into the flocculator, or they can dose the chlorine over here on the filter. So here are the constant level tanks that are used to set the level of the chemicals that are being used to feed the chemical doser. Yeah, I know it's really tiny, but right there's where the chemical dose lever system is hiding. And then here's the entrance tank. Let's see, it's actually the water in this entrance tank is entering right here, going through a trash rack right here, going past the doser where the doser is setting its level based on the flow through the LFOM. Water leaves the LFOM and goes down into the upstream end of the flocculator, goes over all of the baffles in the flocculator. In this case, it's 2 channels, and then enters the inlet channel for the sedimentation tanks, goes down through the sedimentation tanks, goes back up through the flock filter, through the plate settlers, out through these effluent manifolds, through orifices, into the channel that has the clarified water. And then I don't show it in this design because I'm still figuring out how to do this. There's going to be either a pipe or a channel that takes the water from this channel that has the clarified water in it over to this channel, which is the inlet channel for the filter. and then it's going to go through the filter. Okay, we have two filters, which is part of the idea that you really should have two, which is just like the CEPI's design having 12. Do you see that? We said that the CEPI's design, where they have 6 filters working together, they really ought to have 12, so that when you have a low flow condition for your plant, you can still backwash your filters. Same thing here, just that we get that same benefit by having 2, because each of our filters has essentially 6 filters inside of it. And we can always turn one off and send all the water through the other one to backwash it under conditions of low flow. Anybody want to ask a question about how the water goes through the plant? We're all good. So now some more details about the stacked rapid sand filter. Let's see. We're going to talk about the controls. This whole set up here are the controls for getting the water into and back out of the filters. And as you can see, there's a ton of pipes. There are pipes that are inlet pipes and outlet pipes. And if you're remembering how this works, there's the inlets and outlets are every other pipe. So the top pipe is an inlet and an outlet, inlet, outlet, inlet, outlet, inlet. The bottom one is the one that is also used for backwashing. And because the backwash flow ends up being 6 times as much, the bottom pipe ends up being often, not always, but often ends up being a bigger size to handle that higher flow rate. Other kind of fun things that are going on here, the sand in the sandbox is in this box. It's also full of pipes, right? There's going to be lots of pipes inside the box in order to distribute the water and basically inject the water into the sand. And that means that if you ever need to, or when you need to do any service inside the filter box and you want to get the sand out, you can't send workers into that box and give them a shovel and tell them to get the sand out, because the box is actually full of pipes. And so from the very first filter, we knew we had to have a mechanized way, not automated, but a mechanized way of getting the sand out of that sandbox. And the way that we do that is there is a pipe coming out of the very bottom of the sandbox, and it's just like one straight pipe. In this iteration, we don't even have a valve on the end of it. And this is like, there's a little, it's called a Fernco fitting. It's a little like rubber gasket that goes around a pipe, and it has 2 hose clamps that tighten it on. And when they want to empty the sand out of the filter box, they will loosen up those clamps, and this red cap on the end of the pipe will pop off. And what they do is they set the filter up in backwash mode, so the sand is fluidized. And now there's all this fluidized sand that is just happy to flow up this pipe instead. And so it dumps the sand into the sand channel. And so you can empty out the filter. And I guess, you know, if you want to make yourself infamous, you go into an agua clara plant and you open that up when they're not expecting, because it dumps the sand out. And then there's a whole heck of a lot of work to put it back in again. There should be like a lockout on that pipe, so you don't accidentally do that. Another thing that we're adding, that we have not yet built the plant that has the ability to recycle the backwash water, but for your assignment for the design challenge for filtration, I'm going to have you calculate the turbidity of the backwash water. And it turns out that it's less than 100 NTU. And treating 100 NTU water with an agua clara plant or a standard municipal water treatment plant that has flocculation and sedimentation, treating 100 NTU water is just a lovely experience for the operators. It's super easy to treat 100 NTU water. It's actually it's often easier to treat 100 NTU water than it is to treat water that's like 2 NTU. So that means that the backwash water is actually highly treatable. It's not that dirty, and it's a crying shame to waste it, especially if there's a drought. And so we're adding a backwash recycled tank that will take the water from the backwash, store it in that tank, and then before you backwash the next filter, you would use an electric pump to pump that water back up to the entrance tank of the plant. And now you're probably all in shock, right? Because Monroe began this talk by like preaching against the use of pumps. And now I just kind of like slide it in that we're going to use a pump for this. Is Monroe just completely inconsistent? Or what do you think is going on here? Any ideas? Why do I think it's fine to use a pump when I want to use a pump, but otherwise it's not fine to use a pump?
Is it because it's not pertinent to the rest of the plant? Like this pump, like the backwash can still happen without the use of that pump. And so if anything, like the power goes out, you don't need that water. You can still function without it.
It's exactly right. The plant will work just fine if there's no electricity and that pump can't be used. It just means that you won't be able to recycle the backwash water. But when you have electricity and you can pump that water up, that's still cheap water because you're only having to lift the water a few meters to get it back into circulation through the plant and recover that water. So it is very economical to use electricity to recover that water. Okay, so I'm not actually inconsistent. What my line is, I want to be able to operate the plant and provide folks with water without using electricity in the plant. Except for lights, another one. I like lights in the plant too. Okay, so the backwash water flows through this backwash siphon, which we'll talk more about that, and it ends up in this channel. So that's the level that the backwash water is sitting at. And if you want to recover that backwash water, you pull this little pipe stub out, this red pipe stub, and that pipe is connected into this tank. And so the backwash water will flow into that tank instead of being dumped. This is top view of the filter controls. And goodness, there's a lot going on here. So you know where we're at, right? We've gone and we've looked at this set of controls, and we're going to try to figure out how they work because there is a lot going on. So let's follow the water. So the water, remember magically, because I haven't drawn this yet in the design, but magically, maybe we'll use Bluetooth, the water from the clarifier ends up in this channel. Come on, only a couple of you even smiled about using Bluetooth to transport the water across the plant. Okay, so we'll get the water into this channel, and then this channel serves all the filters. And in order for the water to get into one of the filters, it has to cross a wide weir. I should have said wide weir. It's quite wide, and the water flows across that wide weir, and we're counting on that wide weir to distribute evenly the flow between the two filters. So one filter gets its water over this wide weir, and the other filter gets its water over this wide weir. Then there's this intermediate channel that has water in it that's now the flow rate of water for one filter, or in this case, half the plant flow rate is going to each filter. So half the plant flow rate is sitting in this channel. And this little pipe is connected to a plate that is covering up a little slot weir. So there's a narrow slot that the water flows from this channel into the inlet box for the entire filter. And the reason for that this channel, or one of the things that this little channel, intermediate channel does, is if we, for any reason, need to bypass the filter, we put this, we shut the slot weir, right, by putting this plate in front of it, and we would pull this pipe stub out, and now water can come from this inlet channel, go into this intermediate channel, not go into the filter box, in the inlet box, but instead kind of cheat and go right to the outlet. And right here is the pipe that would go to the distribution tank, the clear well, and onto the community. So instead of going through the filter, it's just bypassing. Okay, so I covered the bypass, but that's hopefully not going to be used very often. The real path is to go through this slot weir and then into this inlet box that has 4 pipes leading out the bottom that are going into the filter, and a 5th pipe that is an overflow. So when the water level gets too high, this overflow kicks in and it starts dumping the excess water so that the plant doesn't flood. The water goes into the filter through those 4 pipes and then pops back out of the filter through these 3 pipes. So the water level down here is much, much lower. And the water flows over a tiny weir. So this is a very low weir that the water flows over and goes into this final filtered water spot that is shared by 2 filters. So water is going across the weir in this direction. It's also going across the weir in this direction from the filter on the right. This pipe here will hold a flexible tube that is dripping chlorine. So the chlorine from the dose controller will end up in a flexible tube that will dump out right here, and water will be flowing down into this pipe and leaving to go to the clear well. Wow, was that too much? Maybe. Anybody want to ask a question? Like how does something work, or why? Or did you invent this all in one night? No.
For those slot
Okay.
weirs, do they like slide in and out, or are they like just placed there?
Great question. So the slot weir is very narrow, maybe only like a few centimeters wide, and we're okay. And the plate that covers it is probably going to fit into like a U channel or something, but currently I've not drawn that, and I'm just placing a plate that has a PVC pipe on it as a handle to cover up that slot, and I'm counting on water pressure to hold it in place. That plate to cover up that slot would only be used when you're trying to take a filter offline. It's not used during normal operation. It's your emergency, I'm turning off this filter. And
Gotcha.
we do this frequently, where we use systems to like divert flow that aren't leak tight. Like it's not going to be leak tight when you put that piece of PVC on top of a concrete hole where there's a gap or a slot through the concrete. But it's gonna get most of it. And the fact that it's going to leak a little bit doesn't bother us, because this is just like, you're doing this for an emergency situation. It's good enough.
Gotcha.
Other questions? Okay, I want to take you down another path yet. What do you do when there's enough water? Maybe when the flow rate to the plant has reduced by 50%. How do you make it so that you can just easily backwash one filter? So here's where we play an interesting trick. If there's only enough water to backwash one filter, during backwash, you would like all the water to go to that one filter, right? And the way it's set up right now, there's this broad weir here, or wide weir, and there's one here as well. And that weir is what's controlling the flow to the filter. And since they're both the same, half the water goes across each weir. And so we're not having any way to actually get, we'd like all the water to go to one filter during backwash. So when you want to backwash under low flow conditions, what you do is you remove this gate. So this is another one of those plates that just is held in place on this, at this weir, and you just lift that out. And when you do that, it opens up a much bigger opening into this filter. And now that filter is going to grab, well, what's going to happen is the water level in this intermediate space is going to end up being the same as the water level in this channel, because you opened up this big opening. So the water level here and the water level here is going to be the same. And now we've switched the control point for the filter. Now this narrow weir is designed so that it can handle the design flow rate. And so it will deliver the design flow rate to this filter. Wow, did that make any sense? I changed the point of flow control. It used to be that the flow was controlled by flowing across this weir. And then I basically disabled one of the weirs. I blasted a big hole in it so it gets all the water. And now our second control takes over, and that's this narrower weir that's taller. It's designed to just handle the flow rate that you need for the design flow rate. And so it will ensure that you don't get too much water in the filter to backwash it. And it'll, if there's only half design flow in the plant, it'll take all of it if there's two filters. And the other filter will be high and dry and get nothing during backwash. Okay, here's another thing. This is going to make more sense later on, but there is an extra orifice that's tucked into the inlet that is the backwash inlet. And this is complicated too. This is about making sure that the same amount of water goes in the backwash inlet, the bottom inlet into the plant, into the filter, as what goes in the top inlet under conditions of filtration. So we needed the kind of the loss coefficients or the head loss flowing through the top pipe and the bottom pipe to be the same during filtration. And so but you already know that the backwash pipe is often bigger. And there's some other differences too, because it has to be able to handle the backwash flow, which is all the flow during backwash. So it has to be bigger and there has to be less head loss during backwash. But we needed to have more head loss during filtration so that it's the same as this top pipe. And so the way we adjust it is we add some head loss, we add an orifice during filtration so that it doesn't get too much water during filtration. Somebody want to ask a question about that one? So if I didn't do anything during filtration mode, the bottom of the filter would get too much water because I've designed the bottom path to be less head loss so that, or it's bigger capacity because it's got to handle the total flow of the plant or total flow of the filter when we're doing backwash. Here are a couple slices now, section views, looking at the side of the filter. In this view, we're inside the inlet tank. And so you can see the 4 inlet pipes going down and dumping water into the filter. And so here we can see inside the filter, and we can see that there's complexity inside the filter as well. Okay, so we see the water going in, water going out. Oh, okay, and there's sand. Okay, so if there were sand there, you wouldn't see anything. So happily, I didn't draw the sand, but I put some sand in there just for show. And during that's the height of the filter sand. During backwash, it's going to expand, we estimate about 30%. So that means that our pi backwash over filter is the backwash height of the sand divided by the filter height of the sand. So that number is like 1.3. 1.3 minus 1 is 0.3. So there's this extra height of sand that happens when you're backwashing and the sand is fluidizing. And you'll notice that the pipe, the siphon pipe that takes the water out during backwash is above that level to make sure that we don't take sand out when we're backwashing. And then you also know that the head loss through the sand when you're backwashing is roughly equal to the height of the filter sand. So there must be another height of the filter sand up here, and the water level coming in this box must be higher than that, so that there is enough potential energy in the water in this inlet box to fluidize the sand and then leave through this the siphon pipe. And the siphon pipe, I'll trace it in one of the next drawings, but it ends up over here exiting right at this level. So you can see that there's more than the height of the sand between the water level in this tank when it's backwashing, which is right up here, and where it exits from the siphon. And that energy we need, because we're going to lose that energy fluidizing the sand bed. Here's a cross section through the filtered water tank. So now this is at a different layer. I'm slicing it again. Here we can see that all of these three pipes are bringing the filtered water out. So they're if this top one is 1, they are 2, 4, and 6. Pipes 2, 4, and 6 are the outlets, and they get out of the way by going through a 45-degree bend here, and then they shoot up and go into this outlet box. And do you see that each of those outlets serves exactly 2 layers? Why was I holding up 3 fingers? How about 2? Each of those outlets, each of those 3 outlets is serving exactly 2 layers, because there are 6 filter layers total. If we go back 1, here, each inlet, these inlets do different things. Look, the top inlet serves 1 layer. The bottom inlet serves 1 layer, but the middle 2 inlets, the inner 2 inlets, water can go either up or down. And so they each serve 2 layers. So you're seeing that, these pipes are not all the same. Some of these trunk lines serve 2 layers of sand and some serve 1. Okay, now we're looking at the siphon pipe. This is the pipe that takes the water out of the filter box when we are backwashing. So there are some orifices that you can just barely see here that are on the top of that pipe. They're taking the water out. It goes through, it's a siphon, and we'll learn more about that maybe today. And it discharges right here. And if you look at this pipe, there's something mysterious about it. There are no valves in this pipe, and yet under normal operation, the water level in the filter is up here somewhere. And so the question is, why isn't that siphon pipe just always emptying the water out of the filter? And we'll figure out what the magic is of that eventually. We can also go into the filter box. So inside the filter box, there's a ton of stuff. So this is an end view. Here's where the inlets and outlets and inlet and outlet and inlet and outlet and backwash inlet would connect into this system of the internal plumbing. This doesn't show everything, but it shows a lot of the pieces. These pipes here are receptor pipes. These pipes are branches. And these pipes here we call trunks. And then there are these hose clamps that go around one whole bundle of 2 receptors, the branches, and a trunk. These hose clamps hold it all together because this whole system can be disassembled. It's not glued together. So here are 2 other views of this same mess of plumbing. And I think I'll let you look at that for a minute and ask me any questions you have about what is going on.
I have a question.
Yeah.
The sand, like after this internal plumbing fixture is assembled and put down into the filter box, is that like, do you just kind of shovel the sand in there and hope it makes its way where it needs to go? And also, like, is there any distinction between the layers of sand besides like what we are imagining? I guess like you can see between the pipes, but is there anything that separates the layers?
Great question. So there is nothing dividing the layers of sand. It is one continuous box of sand. And what we're doing is we're sending flow into and out of this sand. It's almost like we have a well field where each of our branches is like a well, and we're injecting water into an aquifer at a whole bunch of points. And then later we're pulling it back out with another well field. So we have wells that are injecting in and wells that are pulling it back out again. And indeed, when I was thinking about how to create this system, I was thinking a lot about injection wells. That's the kind of what we're doing, where we have one big aquifer here with lots of wells injecting and extracting. And you had a question about how do we get the sand in this box? So great question. The way we do it is we fill the box partway up with water so that all of this piping is covered with water, okay? And then the sand comes in bags, and you rip open those bags and you dump the sand in the top. And that's that, and it goes to where it needs to go. And then before you would run the filter the first time, you would backwash it. Usually the sand that you buy has some fines associated with it, so you clean it up a little bit in that first backwash. More questions? Like, do you want to know what is going on in the receptor pipe?
All right, I have one more question.
Yeah.
So the water doesn't actually like enter and exit the sand through the inlet. It goes to the branches. Is that
Correct.
okay? All right.
Yes. So you can see here that the inlet pipes have holes in them. And I'm not showing everything in this view. I'll show more. Well, let's go to the next slide just for a second. Inlets and inlet branches look like this. So I'm not showing everything in the previous drawing because that's still under construction from my perspective. But each of these white, and actually this gray one as well, these branches with holes in the bottom don't look like what I've shown there. They look like this. So there's a pipe with holes in the bottom, and then there's this wing, which is exactly half of a pipe that's glued onto the main branch. And wow, and its role is to prevent sand from getting into those orifices when the filter is in backwash mode. So water is normally flowing out of these holes into the sand. So that should be fine. There shouldn't be any sand migrating up into these holes during filtration mode. But in backwash mode, it would be just too easy for some sand to get up into this pipe. And so to protect the pipe from getting any sand in it, we add this wing on the bottom. And then when backwash is happening, if you think about what's happening, you can imagine this being a fluidized bed of sand, and water is coming up through here. I should have drawn lots of arrows. Water is going up through the sand to keep it fluidized. And that would mean that the sand would be everywhere. But in here, inside this hemisphere, or what is this? This half cylinder, there's no upflow velocity, right? There's no water going up through that pipe. So the upflow velocity in here is 0. And that means that any sand that gets into this zone has a terminal velocity that the sand has, and it settles back out. And so this zone underneath this half pipe remains clear. And so there's no way for sand to get into this pipe. I'm going to go back to this view. Ask me more questions. Okay, it's 5 after 3. We're at a fine place. Let's see, let me take you, I'm not going to show how we actually initiate backwash, but I'll show you the other kind of branch. So you see how these work. These are the outlet branches. Here, the water is going from the sand into the pipe. And the way that we prevent the sand from getting into the pipe is we have pipes that have 0.2 millimeter slots cut in them. I don't know if you've thought about 0.2 millimeters lately, but I think it's pretty similar to the thickness of your thumbnail. You can go check that on the internet and see if I'm right. But it's like you have to work to get your thumbnail into these slots. Okay, so really thin slots, so thin that the sand can't get in. And so this is the same system that is used in wells, where if you have an aquifer that's got sand in it, you can put a well screen that is just PVC pipe with these slots in it, and that will prevent the sand from your aquifer from getting into your well, and you'll have clean water in your well. So we're using that same idea inside the filter. Remember I told you I was thinking about what we're doing inside this filter like a well field with lots of wells in it. So here's one of my wells. It's got a well screen. Literally, it is a well screen. And here's another detail. Look at this. There's this crazy molded curve on the end of this pipe. That molded curve is going to connect to this receptor pipe out here. So here's the receptor pipe, and the branch fits into that receptor pipe, and the curve of the receptor pipe matches this crazy curve here. So the hole in the receptor pipe is drilled to be exactly the same diameter as what I have my mouse on. And then this branch slides into the receptor pipe, and it hits everywhere at once along this curved surface. Why did we do this? Well, we wanted a positive stop for one, so that because we're going to hold this together with a clamp, and we need this branch to not rotate. Because if this branch rotates, the wing won't be doing any good. The wing has to be pointed down in order for it to work. So if the wing were pointed up or to the side, it's not going to work anymore. So we have to keep this branch from rotating, and it's that curved surface that keeps this branch from rotating. That's one. Then here's the slotted pipe. Slotted pipe also has that same shape on it. And my question to you is, can you think about why? Is there any reason why you wouldn't want a slotted pipe to rotate? Like, who cares which way the water enters this pipe? But it actually matters. Anybody think about properties of a slotted pipe? I wish I had one here to show you. If I had a slotted pipe in my hand and I went like this to try to bend it, in one direction, I can bend it really easily, and I turn it 90 degrees and I can't bend it. The orientation that we see with in the top one, with the slots on the side, you can't bend it vertically, but you can bend it horizontally. That makes sense? I've made a weak structure into one direction. And what forces do these pipes have to withstand? At the beginning of backwash, all the sand is pushing up on these pipes, and they're going to bend, and they are going to bend. And so we need them to be full strength. And so we need the slots to be coming out the sides and the strength to be in the vertical direction. So we can't let these rotate either. With that, I'm going to break. I'd like to send you to gather. I'm going to come around to each team. And what I would love to have you do is you can each pull up the PowerPoint presentation, right? It's on the syllabus. It's on the syllabus. And I'd love to have each team just like talk about what you learned today and raise any questions. And then I'll come by and see if I can answer any questions. Okay?